Dear students, let us now come to uh, the next topic, which is of moments and couples. Um Moment, as you are already aware of, it is force into distance. On the distance in this context is distance from the application, the point of application of the force, and the point from where you want to measure the moment. So moment, the sign for moment, the sign convention generally used is for clockwise moments we use a notation negative, and for anti-clockwise we use notation as positive. Okay, so let us directly move to the topic, which is in section 3.4, equilibrium conditions for bodies under coplanar non-concurrent forces. So as we have discussed in our previous topic on system of forces, where we discuss about the coplanar and concurrent forces, and in those problems we have not taken into account the moments, but here, because the systems are the forces are coplanar, but the forces are non-concurrent, that means they are also applying some kind of a moment on the body on which they are acting. So in this context, therefore, we will have to take care of the components, the horizontal components, the vertical components, as well as the moments. Moments, for that matter, we can take into about any point within the plane of in which the our problem is lying, or in which the forces are acting, because the forces we assume are the coplanar. So if the equilibrium conditions are to be applied, that means the body is in equilibrium even after the application of these forces, then the horizontal sum of the horizontal components of the forces will be equal to zero. Sum of the vertical components of the forces will be equal to zero, and sum of the moments will also be equal to zero. So these conditions will be applicable in case of equilibrium conditions. Now, Varignon's theorem, it says states that the algebraic sum of the moments of two forces about any point in their plane is equal to the moment of their resultant about that point. Which means that if we take the moments of the forces individually and sum those up, and if we take the moment of the resultant, considering the point to be same, the point in both the cases should be the same. That means the point when we are taking the moments about that point of all the individual forces, and the moment when we are counting the resultant force, so that should be the same. So in this section 3.5, the proof of that theorem is given, the derivation of that theorem is given, so you can go through that. And let us discuss the system of forces which are parallel. In the first case, in the section 3.6, first number, the resultant of two like parallel forces will be found like this. So in this case, you see, you have the two forces, basically force P and force Q, which are parallel to each other, and they are in the same direction. Okay, so let us say that their resultant is passing through a point C. Okay, so the resultant force will be equal to R is equal to P plus Q. Now, to find out the point of action of this resultant R, that is point C, which is lying in between A and B, somewhere in A and B, but we don't know what is the distance of this point C from A. Simply, we have to find out the moment of the forces acting at A and B, so that the resultant moment is zero as it passes through C. Okay, there is the moment about C. So in this derivation, it is given over here, and you will ultimately see that the point C will be because the net effect of this moments of force P and force Q is to be equal to zero at point C. Uh, the point C will lean more towards force which is larger in which is higher basically. So if P force is higher, the C will lean towards point A, because the moment of P into the distance, whatever the perpendicular distance is, will be lesser, and with respect to the force Q, the moment can only be balanced if we increase the distance, that is Cn. Okay, so this is given in this derivation, and you can go through that, because I want to spend more time on the examples. So second case is a resultant of two unlike parallel forces. So in this case, you see in this figure 3.10, the force P is acting in this one direction, and force at B, that is force Q, is acting in the reverse direction, but both are parallel. Again, by taking into account the moment of the force P and force Q, you can say that the point C in this case will be somewhere outside A and B. That will be outside A and B, because the because if the force P is larger, the resultant will be P minus Q, and the moment of this P about this point, because P is larger, this will be moving outwards towards the point A, so that the force P into the distance, whatever the perpendicular distance between this A and the resultant line, between the force P and the resultant vector, will be equal to the other moment which is caused by the force Q. Okay, so these are just you can find out mathematically, as well as otherwise also you can see that these things, or the results which we are getting here over here, make sense in when we correlate things physically. Okay, so let us now discuss the next topic, which I'll be discussing in the next video. Thank you.